Hello? Hello? All right. Good morning, everyone. I think it's time to start. So, first of all, on this Thursday, this is from the request of the feedback in our midterm. Students want to some more guidance about how to debug and some introductory content about the common use libraries, especially in Python. So we have arranged a lecture given by our TM, Shikai Fang. He's gonna use his own experience. He's an excellent PhD student, has been using those machine learning libraries and languages for years. He's gonna use his own experience to showcase how he implemented debugging the machine learning models and test it on real data and how to conclude that his code is correct or not. And in addition, he's gonna introduce the common used libraries, extremely common in Python, like NumPy and SciPy. And he's gonna explain how you should leverage the documentation of those open source libraries, especially like SciPy libraries. It's pretty comprehensive and detailed. But our experience is that, okay, it seems that many students kind of like ignore the documentation or are not aware of the documentation. Actually, there are detailed examples here. You can follow them. You won't be confused about how to use those libraries. But anyway, Shikai will provide some examples to give you a hint of that. So hopefully, this will be very helpful for the remaining homework assignments and the course projects, especially when we do the program portion. Okay, so let us continue with SVM. So in the last lecture, we introduced the dual formulation of SVM. Right? So it originates from the general primal and dual formulation for constraint optimization problem. Right? So for an arbitrary constraint optimization problem, we can first convert it into a minimax optimization problem over the Lagrange function. Right? You're gonna optimize both the model parameters and the set of Lagrange multipliers, which corresponds to the constraint functions, right? And then you just switch the order of the mean and max. Then you get the dual formulation. So the primal problem is to solve min and max, while the dual form is to solve max min, right? So we can apply this general formulation for SVM. Right? So this is a primal form of SVM. We know that this objective function is a regularizer plus a summation of the Slack variables. Right? Remember, Slack variables aim to enable some examples to break into the margin. Right? And also have a hyperparameter C, which should be manually set. And then for each example I, we're going to introduce two constraints, right? First, the Slack variables, the CI must be non-negative, and second, the function margin must be no less than 1 minus the CI, right? So these two constraints together allow the example xi to break into the margin. Right? If the CI is 0, then it means that the function margin is bigger than or equal to 1, right? That basically says, okay, the xi should stay on or outside margin. Right? Remember, the key idea of SVM is that, okay, I'm going to allow some outliers to be excluded. Then I'm going to find a classifier to correctly predict all the remaining examples. Right? In other words, this remaining majority of the examples will be separated by our hyperplane, and we'll find maximum margin for this separator, meaning that all those majority examples should stay on or outside the margin. Right? And only a few outliers whose CI can be positive, right? Meaning that when they satisfy these two constraints, it indicates that they stay inside margin. And then we just follow the standard definition, right? Primal problem, we introduce Lagrange multipliers for the function margin constraint Fi, and for the non-negative constraint for the CI, so it's beta I. So we can construct a Lagrange function here, right? And then we put the min and max in front of this. So this is the primal formulation of the SVM. So remember, in the inner level, we're going to maximize the Lagrange function with respect to non-negative Lagrange multipliers. So this is an important constraint. Right? And but for the outer level, we're going to minimize this Lagrange function with respect to the model parameters, which include the feature weight vector W, the bias parameter B, and also this Slack variables. Right? And then we just switch the order of min and max. In the inner level, we minimize Lagrange function with respect to model parameters, and in outer level, we maximize with respect to the Lagrange multipliers. So this is called a dual form of SVM. Right? So we want to analyze the solution of the dual form to get more insights from the SVM solution. Right? So how can we do that? Of course, we don't want to deal with this max-min optimization directly. That's too hard. So we're going to do some simplification, mathematical simplification, right? So we're going to first fix the Lagrange multipliers outside, then we solve the inner minimization problem, right? This is straightforward. Just take the gradient of the Lagrange function, set the gradient being 0, you got a bunch of results, right? You got the optimal, you got the weight vector should be a linear combination of the training inputs weighted by the Lagrange multipliers alpha i's, right? And also two other equalities implying that the gradient with respect to the bias parameter B and every Slack variable should be 0. And then you just substitute those results back into here, right? You've got a solution for the minimization, inner minimization problem. So you can simplify the dual problem into a quadratic optimization problem, right? Of course, we need to respect these actual constraints when you doing which is from the intermediate simplification step. So now, of course, you can flip the sign, or you take the minus in front of it. It is equal to minimizing this, right? And by some compact representation, our final dual form of that theorem is like this. So this is typical quadratic optimization problem. This is a classic problem in convex optimization. You don't need to know. If you're interested, you can take a look, but you don't need to know how they're going to be solved. But the objective function is essentially a quadratic function in that it is a double summation over the training examples, where each summon is just the corresponding alpha I times alpha j times the labels yi, yj, and times the inner product between x and xj, then subtracted by the summation of alpha I. And of course, you need to respect the two types of extra constraints. This is pretty easy to solve. You can use any off-the-shelf convex optimization library to solve them, right? And the motivation for us to look into this dual formulation is that we'll see some important solution structures. And also, this solution structure will enable us to inject the so-called kernel trick and to extend SVM from a simple linear classifier to much more expressive nonlinear classifiers. But before we get into that, we need to first know, right? Because in solving the dual form, we'll only get the optimal Lagrange multipliers alpha 1 to alpha n, right? If n is the number of training examples. And we want to know how can we recover the optimal model parameters WB from it, right? That's the first issue we need to address, right? As we discussed in the last class, to recover W, it is relatively straightforward, because when we simplify this max-min dual formulation problem, we get this relationship, right? We know that W must be a weighted summation of all the training inputs, where each training input is weighted by this alpha I times the label yi, right? By the way, please be aware, yi must be either 1, minus 1. It is not 0, 1. Right? So just keep it in mind. Otherwise, you're gonna zero out many training inputs, right? And so, if you want to get optimal weight vector W star, you can simply substitute the optimal values of alphas to alphas, right? And then the remaining question will be, how can we recover the optimal bias parameter B, right? And unfortunately, this is not trivial, because the intermediate results, right? Because the intermediate results, when we solve inner minimization problem, if you take the gradient with respect to B being 0, because this objective, this Lagrange function is linear to B. So if you take gradient B, well, the remaining thing must be 0, but it has nothing to do with B. So you can't use those results to recover B. So we need to leverage extra knowledge. Right? What kind of extra knowledge should we use? We're going to use the so-called Kdp conditions. Right? So Kdp conditions are kind of a fundamental concept in optimization theory. Right? Briefly speaking, you can view them as a set of testing conditions associated with some constraint optimization problem. Right? So here, for simplicity, we just talk about the Kdp conditions for convex optimization listed here. So we assume the objective function is convex and all the constraint functions are convex. But there are Kdp conditions for general optimization problem. Right? So among those test conditions, one type of very important and useful condition is called complementary slackness, meaning that for every Lagrange multiplier lambda m and the corresponding constraint function, we require their product is 0. This will be very useful. We're going to discuss in a moment. So if you have a pair of x, which is the input variables in the objective function, and also a set of Lagrange multipliers, which correspond to those m constraints, right? If they satisfy these Kdp conditions, what conclusion can we draw? A good conclusion, which is called sufficient condition, meaning that the x and lambda will be the solution to this objective function, to this constraint optimization problem. In other words, if we can find a pair of x and lambda which satisfy this set of conditions, we can conclude x is the solution of this corresponding constraint convex optimization problem. But the reward way does not hold in general, meaning that you can now say if I am given the solution of this, there exists a corresponding Lagrange multiplier of lambda where the pair of x and lambda satisfy the Kdp conditions, meaning that they're only sufficient, not necessary. It's like, okay, suppose you're given a free function, right? And oh, sorry, that's not a good analogy because the gradient being 0. If it is a solution, then the gradient must be 0. But if it's gradient 0, it does not necessarily correspond to a solution. So it's kind of similar in the high level, meaning that the KKT condition is kind of one side, one direction conclusion you can draw from that, but you cannot draw in opposite direction. Right? But someone may ask, in what cases KKT conditions can be both sufficient and unnecessary, meaning that for any solution of this constraint optimization problem, there exists a corresponding lambda such that they satisfy the KKT conditions. In that case, you have to simplify the form of the constraint functions. So if your constraint functions are all linear constraint functions, meaning that your constraint functions or your all constraints can be written as a kind of vector inequality in this form. Right? Left-hand side is kind of constant matrix A times your input variable x, it being bounded by B. Right? If your constraints can be written in this way, then KKT conditions are both sufficient and necessary, meaning that if you have a pair of x and lambda, they satisfy KKT conditions, they are the solution. And also, vice versa. If you have a solution x for the optimization problem, then you must be able to, there must exist some lambda such that x and lambda satisfy the KKT conditions. So why should we emphasize this? Right? In addition to be more rigorous, we want to emphasize the nice property of SVM. Because the SVM problem satisfies this form. Meaning that KKT conditions are both sufficient and necessary conditions for SVM objective to find the solutions. Right? This can be easily verified by looking into this private form, right? So you can see all the constraint functions in SVM primal are kind of linear, right? So it's not hard to rearrange them into the form of this Fn inequality. So that means, suppose if we use any approach and we're able to obtain a solution of SVM, then this solution must satisfy the KKT conditions. You see the point? Right? The solution must satisfy the KKT conditions, meaning that all those 4 types of conditions apply to those solutions. That means those conditions can be viewed as properties of those solutions, so we can leverage these properties to inform our optimal bias parameter B. Any question regarding the underlying logic? Is everyone comfortable? Yeah, I mean, in a nutshell, we know from the optimization theory, we have actual properties of those solutions which can be represented by KKT conditions. We're going to use those properties to recover our unknown bias, optimal bias parameter B. Okay, so now let us look at how can we do that. So we're going to use 2 types of complementary slackness, as we mentioned. they are very useful Kdp conditions, right? And combined with the intermediate results, when we derive the simplified form of the dual, right? We combine them together to infer the bus parameter B. How can we do that, right? So first, let us look at the complementary slackness. Right? We know that for the optimal Lagrange multipliers alpha I star and beta I star for each training example I, we got the product between them and their corresponding corresponding constraint functions being 0. So meaning that, okay, for each training example I, the beta I star times the C I star equals to 0. And for each alpha I star, we got alpha I star multiplied with this constraint function. Remember, the constraint function is the function margin subtracted by 1 plus the constraint plus the slack variable. Okay? So it comes from here. So, and also we're going to leverage this intermediate results when we simplify this bi-level optimization problem, which is dual problem, right? When we take the gradient, when we solve the inner minimization with outer level phase, we get alpha I plus beta I equals to C, right? So we're going to use these results. Right? And now, let us put them together and see how can we smartly use them to recover our optimal parameter B, right? How can we do that? We know for every training example I, we have all the three equalities whole, right? And then we're going to look at some training example J, such that the optimal alpha J, namely alpha J star, is strictly between 0 and C. There's no equality. It must be bigger than 0 and strictly less than C. And then let's see what can we get. Right? All of these are three results, right? So first, we know that this is the intermediate result, right? When we solve the inner minimization, when we simplify the max min problem, right? We know that alpha J star plus beta J star must be big C. Right? Big C, remember, it's a hyperparameter trade-off between the regularizar and hinge loss. So now, because alpha J star is strictly less than C, and then beta J star is C minus alpha J star, will be strictly bigger than 0. Right? It comes from here. And now, if we look into the complementary slackness regarding beta J, right? So we know beta J star is bigger than 0. To make this product 0, we must have the slack variable be 0. In other words, the optimal slack variable for example J must be 0. This is the first result we can get. And now, from the other side, right, alpha J star is strictly bigger than 0. If you look at the complementary slackness regarding alpha J star, look at here. Right? Because alpha J star is strictly bigger than 0, to make this product be 0, you must have this constraint function be 0. Right? Right? If the constraint function be 0, right? And now that means this function margin subtracted 1 plus this optimal slack variable be 0. But from our derivation, right, we know that the optimal slack variable is 0. So we got this equality. Namely, the function margin subtracted by 1 must be 0, right? So now we know the W star, right? We have already recovered W star by the linear combination of the training weights, training inputs weighted by those alpha I stars, right? So to solve B star, we can just subtract the label Yj by this inner product between the optimal lead vector and input training input xj. So now we can see if we can find some among training data, if we can find some training example whose corresponding alpha G star is strictly between 0 and C, then we can very easily recover the optimal bias parameter B star. Any questions so far? Yeah, this is a kind of like a mathematical reasoning. It's easy, but it sounds like a little tedious. You can just you need to know. Okay, I'm gonna combine those conclusions together, from which we can derive where we can calculate B star. Any question, or is everyone comfortable with that, or feel this too easy? No question? Okay, sounds like it's too easy, right? So anyway, if you feel a little bit, not catch up, not being able to catch up, it's fine. You can just look at the slides for 3 more minutes. You'll get it. It just list all those results together. We know, okay, the optimal solution must satisfy the complementary slackness and also satisfy this, and then we combine them together. We can estimate B star. And someone may ask, like, what if I have many training examples whose alpha G star is strictly between 0 and C? And in theory, using any of those example, you can recover exactly the same B star, but that's just in theory, because in practice, due to the optimization, tolerance level setting, the numerical precision, and all kinds of stuff, they might have some variation across the B star estimated from different examples. And so for the robustness, we can just average those results. Okay? So now, after we have talked about how to recover the optimal V vector W and bias parameter B from the dual solution, right? Remember, dual solution are mainly this optimal Lagrange multipliers alpha Einstein. They want to look into the structure reflected from optimal V vector W. So from this, we can see that given the optimal solution for the Lagrange multipliers, the optimal weight vector is a weighted summation of all the training inputs, right? And the H training for Xi is weighted by alpha I star, of course, multiplied the label Yi, right? Either 1 or -1. So a natural question would be, what if some alpha G star is simply 0? Suppose, for example, alpha 1 star is simply 0. What does it mean? Any thought? Any guess?
It'll just zero out that term in your sum.
Yeah, exactly right. So if for some training example the corresponding alpha G star are 0, meaning that they actually have not any influence on the optimal V vector. Right? In other words, they are zeroed out from the summation. So we can see that although the optimal V vector seems to be the linear combination of all the training inputs, right? But W star is only determined by those examples whose alpha G stars are non-zero. In fact, practical applications show that, for all kinds of SVM applications, most of the training examples, their corresponding alpha G stars are 0. So the optimal V vector is only determined by samples with non-zero alpha G star. So we call this subset of examples as support vectors. That's where the definition of support vectors come from. Why? Because it is them who determine the optimal V vector. It supports they support the weight vector. That's why they call support vectors. So if we denote the set of support vectors by S, right? X are all the training inputs whose corresponding RG star is strictly bigger than 0. Then our weight vector, optimal weight vector, is essentially a weighted combination of all the support vectors. And the support vector, each support vector is weighted by the RPG star. Of course, you need to account for the training label. Right? So where do these support vectors living? What are their positions? To answer this question, we need to use the Kdp conditions again, namely the complementary slackness. So according to the complementary slackness, we know that for every example J, right, we got this RPG star. This is Lagrange multiplier, multiplying with the constraint function B0, right? So for a support vector, we know that RPG star must be strictly bigger than 0. Right? So that means the constraint function must be 0. That is, the function margin is y multiplied with the prediction score is equal to y minus slack variable CG star. But remember, the CG star is always non-negative. So that means your function margin must be less than or equal to 1. So this inequality actually determines the position of the support vectors. So I want to ask, what are their positions? Where do they locate? Relative to the separating hyperplane. Where do they locate? Any thought? If an example satisfies this inequality, namely the function margin is less than or equal to 1, where do they locate? Any guess? Yeah, give me a guess.
Are they inside the margin that you started with?
Yes, exactly right. So remember, in the formulation of parts SVM, right, we require every example to be separated and to stay on the outside margin, right? That is expressed as the inequality that the function margin must be bigger than or equal to 1, right? Remember, that's our formulation, right? We restrict our weight space such that their minimum distance is 1, right? So that means for every example, the function margin must be no less than 1, right? That's our formulation. And then we move to soft SVM. We allow some examples to break into the margin, meaning that example, they can make the function margin to be less than or equal to 1. Right? So if it is equal to 1, well, it just means that example stays right on the margin. But it's less than 1, means that it breaks into margin. It is inside margin or intrudes margin. Only when it is outside, it is bigger than 1, means it is outside margin. So now we can see that for support vector, the function margin is less than or equal to 1, meaning that the support vectors must be inside margin or right on the margin. So this is a very important observation, right? So now you can think of this. It's funny, right? So remember, support vector, the soft SVM, right? To account for the nonlinear separability of the data, right? We intentionally allow some examples to be viewed as outliers, meaning that they are allowed to break into the margin. Right? And then we want to separate out all the remaining examples and then use a hyperplane with as large margin as possible to separate them out. Right? Meaning that the majority of examples are outside margin. And only a few outliers can break into the margin. And now, the position of this hyperplane are actually determined by those bad guys, by those ROIs, not those good guys, the majority points which can be well separated by your plane. Yeah, that's the interesting observation from the solution structure. So, as a practice, I want you guys to really get into the analysis, right? Using complementary slackness to analyze the locations, right? So, if a support vector stays strictly inside margin, what's the value of alpha G star? I can tell you the result is alpha G star will be big sig. So remember, alpha G star is bounded by sigma. So that means if the support vectors really breaks into the margin, not right on the margin, the weight of that support vector will be the maximum value. In other words, it's gonna have the maximum influence about the position of the separating hyperplane. So as to why, when the support vectors stay inside margin, you got alpha G star equals to C. This will be left as an exercise 3. But the interesting thing will be, okay, if the point breaks into the margin directly, it will have the most influence on the final weak vector. In other words, the position of the hyperplane. So now, a concrete example, right? More intuitive examples to showcase where the support vector is located. Right? So here are the training examples, most positive examples, negative examples, right? Of course, this data is not linearly separable. So we're gonna find a hyperplane where, excluding a few outliers, most of the examples are still well separated, right? And we find a hyperplane with maximum margin to separate out the most positive and negative examples. And the optimal V vector, which is black line here, is essentially determined by a few support vectors which stay either on the margin or inside margin. On the contrary, for most good points which can be well separated, like here, you can show that their corresponding alpha G star is simply 0. As to why, again, this will leave as an exercise 3. You can show that. For all the examples outside margin, you must have this optimal alpha I star to be 0. So now, this explains why in practice the solution tends to be very sparse. Namely, for most of the training examples, their corresponding alpha I star is simply 0. Why? Because most of the training examples are well separated, right? And by the maximum margin, meaning that most examples stay outside margin, and then you can show their alpha I star is simply 0. And the support vectors are only determined by a few outliers in the training set. They can be on the margin or inside margin. Okay, any questions so far? With the definition or insight from the solution structure and support vectors? Another benefit of this solution structure is that, okay, I can use only a few points which are support vectors to recover the V vector. Right? So one might feel like this is not useful because why not just directly store the whole weight vector, right? Why should I store support vectors? You see that would be very useful. If you want to extend your linear classifier to nonlinear classifiers, you're gonna do some feature mapping. If in a mapped feature space the dimension is too high, that means the computational cost is really high. Sometimes it's infinite dimension space. That means you cannot directly calculate or store the weight vector, which is infinite dimensional. In that case, it's better to preserve support vectors in our original feature space. So we're going to talk about right now. Okay. So now the new form is useful in that it reflects the solution structure of the optimal weight vector and also bring the concept called support vectors. Next, we're going to talk about a class of very useful and important approach. It's called Kernels and Curvatures. So you'll find that kernel tricks are widely used in machine learning. Their major advantage is that you can easily extend linear classifiers to nonlinear classifiers by some feature mapping. However, an expressive feature mapping is usually very high dimensional. So kernel trick can help you to largely reduce the computational cost. Okay, so back to the solution structure. Right? Suppose we solve the new form of SVM. We know that the optimal weight vector can be represented by this weighted summation of the training inputs, where each training input is weighted by this alpha I star. Right? Of course, any alpha I star is equal to 0. Right? So if we use this solution structure to make prediction, what can we get? So in a prediction for arbitrary new input x, right? If you want to make a prediction, we first need to compute this prediction score, right? The inner product between the W star and the test input x, right? Now we'll substitute this linear combination for W star. We get that this inner product is essentially a summation over all the training examples, where each summon is the inner product between the training input and the test input. And then multiplying the optimal multiplier of our I star and also the label y actor. So that means if we leverage the solution structure to make prediction for any new input x, we do not need to explicitly compute the weight vector, right? We just need to compute the dot product between every training example and this test input. So, and this is true even after you perform some nonlinear feature mapping or transformation. Meaning that, okay, if your data is not linearly separable, right? No, now I want to make some smart feature mapping or transformation in some higher dimensional space, right? So each training input. Sorry. Pointer is running out of battery. Let me switch to another one. So each training input or test input is first mapped into a new feature space, right, by this mapping fig. So you can imagine you train a new classifier means newly feature space. You got a hyperplane on that, right? You got a weight vector. So if you want to make prediction in a new feature space, you can apply the same result, right? So the inner product between your weight vector and your map feature vector is also a summation over the training examples, except that each summon now is the inner product or dot product between the map feature vectors. So why this is useful, right? Because later we'll see this can be really expensive. And the kernel trick can avoid you from directly computing the feature mapping and dot product. Okay, this is just to help you refresh the mind, right? Around here, if the original feature space is not linearly separable, we're going to come out some higher dimensional feature vector using mapping speed. In this map feature vector, we can train, you can imagine this 4-dimensional feature space, we can train a linear classifier to have a good hyperplane, while separate all the training examples. So when you make a prediction, well, you need to first perform feature mapping, then use the big vector in that 4-dimensional feature space to make prediction. So now, we can see that if we want to leverage the solution structure from the due form, right, we need to compute the inner product during the prediction. We need to compute inner product between every training example and the test example up to the feature mapping. Right? So now let us define this result as a function of the inputs x and z. Right? For any two inputs and z, we define the result that you first map x through phi and map z through phi to this new higher dimensional feature space, and then do the dot product in a new feature space. This value we denote as the function value of these two inputs or two arguments x and z. So our prediction with this high dimensional leaking mapping can be written in this way. Right? So we just replace W by, the result, the solution structure we obtained from due form, which is the weighted combination of the map feature vector, right? You just apply the definition here. This is essentially a summation over the training example. For each example, you got alpha I, y I times this function of xi and x and plus y prime to b. So, what's the usage of this new formulation? This is a natural question if someone asks, right? If to calculate the value of the function k, we're going to still perform the explicit feature mapping phi first, and then do the inner product, right? Like what the definition does. Then this formula is nothing but a notation sugar, okay? Nothing else. There's no actual gain from that. But what if I can compute the value of k in another way? Never need us to explicit computing phi and dot product. Instead, we can compute this function k value in a much simpler way. If you can do that, that will make the prediction much cheaper, right? That's the idea. So one might think, okay, what's the matter, right? So, well, if your feature mapping is not very high dimensional, just 2 or 10 dimensional, that's fine. Nothing worth our attention. But what if your feature mapping phi here is very, very high dimensional, like 1 million dimensional or 1 billion dimensional? And later we'll say some kernels corresponds to infinite dimensional feature mapping. Right? Then the explicit computation of phi is very, very costly, even infeasible, not to mention their inner product. And then the trick to cheaply compute the value of k becomes much more important. That's the completion key. And if you have such a method to compute the value of k without performing this explicit feature mapping dot product, this is called kernel trick. If we can compute the value of k without explicitly writing the blowout representation, then we'll have a completion of the boundary. So this trick is called the kernel trick. And to showcase why kernel trick is useful, we're going to use this example. It's called polynomial kernel. Suppose we're going to treat example x and z, right? We come out a feature mapping, right? map them to a high-dimensional feature space, suppose just a quadratic feature mapping. So what's the definition of quadratic feature mapping? Okay. Suppose you have n features, right? So you're gonna enumerate all possible terms from degree 0 to degree 2, including their combinations. So you can imagine there can be many. Right? So if you write them out, there'll be a long vector. So the first part will be all degree 0 terms. You know, if you pick any term to the power of 0, well, which is simply 1, right? So only one degree 0 term. And then all degree 1 terms, which are the original features. And all degree 2 terms. So degree 2 terms are just combination of all the cross combinations or self combinations of those features. So how many degree 2 terms do we have? N squared, right? Yeah, if you want to deduplicate, well, it will be less than n squared, but it's still proportional to n squared, right? So you can see that after feature mapping, your n-dimensional input becomes proportional to n squared dimension. Right? So suppose your n is 1,000, the n squared will be 1 million. Right? So even for this quadratic feature mapping, you can make your mapped feature vector to be very high dimension. Right? If you want to explicitly compute them and the dot product, it is expensive. Right? Not to mention, people in practice really use quadratic mapping because it's less expressive. Where we usually use high order feature mapping or even infinite feature mapping. So if we directly compute the feature mapping first and then do the inner product, it will take time complexity like n squared. Why? Because your map feature vector is like proportional to n squared dimension, right? And then you can imagine you do this twice for x and d, and then do the inner product. Right? You need to do the element-wise multiplication as I'm forgetting. Right? It will cost like the time complexity n squared. Right? So now, what if I do not explicitly compute this quadratic feature mapping? Instead, I'm going to just compute this function instead. So what kind of function? We only compute the dot product between x and z in the original space. We do not perform any feature mapping. And then we add 1 to this dot product that takes 1. We get a value b. So now I want to ask, what's the time complexity to compute b? And what's the time complexity to compute b?
Should be n.
Yeah, just n, right? Because x is n-dimensional, right? Z is n-dimensional. What are the inner product? Remember, you just do the element-wise product between n pairs of elements, right? And add them together, just take O(n), right? And then you add 1, take squared, just O1, right? So together they're gonna give O(n) time complexity. But if you perform explicit feature mapping and then do the inner product in a map feature space, as we just analyzed, the time complexity is O(n) squared. Right? So imagine what's the difference between them when you take n to be simply 1,000. Right? It's 1 order of magnitude faster, right? And even better thing is that the 2 results are equivalent. Of course, you will see some mismatch in the coefficients, but it is a trivial issue. It can be easily addressed. So this is the power of Kernel Trick. If I can compute the value of k between these 2 arguments using a much cheaper way, and instead of following the exact definition, it can save a lot of computational complexity and space to store those mapped feature vectors. Right? This is called kernel trick. To show why this is true, let us make some properties. Right? Okay, so this is our B, right? And this is our A. And for simplicity, we're going to use a two-dimensional feature vector, namely n here is 2, right? So you've got x to be x1, x2, and z to be z1, z2, right? So obviously, you've got phi z1, z2. You just write out the feature mapping, follow the mapping of x, right? So z1, z2, z1 square, z2 square, and z1, z2, right? So let us first look at the result of derived computing, right? So if you first do the feature mapping here and here, right, and then do the inner product, what kind of result do you get? So it is kind of trivial. So I'm just writing down the inner product between this mapped feature vectors, right, which is simply 1 plus x1 z1, x2 z2, x1 square z1 square, x2 square, z2 square, and finally this term and this term, right? Multiply together, x1, x2, z1, z2, right? This is A. And how about B? Okay. So to compute B, we never need to perform explicit feature mapping, right? Let me use another color. Right? So we first compute the dot product between x and z in an original feature space, which is 1 plus x1 z1 and x2 z2, right? Here is z, here is x, right? The inner product is simply x1 z1 plus x2 z2, and then you take square, right? Okay. So now just to expand this square summation. Right? For convenience, we just take the square of the terms in the summation, right? Which is 1 square is 1. x1 z1 square is x1 square, z1 square, x2 square, z2 square. And then you got to get the cross terms, right? And you have to multiply the cross terms by 2 because you're going to be added twice, right? So the cross term here and here, you got 2 x1 z1. Similarly, this here and here is 2 x2 z2. And finally, this one is 2 x1 x2 z1 z2. Right? So now let us just contrast A and B. You see that all the terms in A are all the terms in B. Right? So you got 1 here, x1 z1 here, x1 z1 here, x2 z2 here, x2 z2 here. More square term, x1 square, z1 square, x1 square, z1 square, x2 square, z2 square, x2 square, z2 square, and x1, x2, z1, z2, x1, x2, z1, z2. Right? They're the same except that, okay, the coefficients are a little bit mismatched here, right? But this can be very easy to fix because you can make your feature mapping. Like here, you can put say square root here and square root here, and and correspondingly, then you multiply with phi. When you multiply phi of A, phi of x, and phi of z, their inner product will be exactly the same as B. Any questions so far? So I will practice this. I mean, although it's kind of like simple and even silly, but just to show why this is useful. Because to obtain the same value, right, you don't need to follow the original definition. You can compute it in a much cheaper way. If you can find a much cheaper way to compute this k, then you win. You save a lot of computational complexity, and you don't need to explicitly store this mapped feature vectors. This is called Kernel Trick. Any question? Or is it trivial? Conceptually trivial, right? Okay. I will recommend you to follow my practice and to sense how the kernel trick takes effect. Anyway, let's go back to the slides. All right. So now, here's a little bit warmer description or definition of kernel trick. So suppose we wish to compute a function of k of two arguments, right, which is the dot product argument matching x and z to some new feature space through k. The kernel trick is that we can save the time and space by computing this value k by performing operations only in an original feature space. No need of performing the feature mapping fit. This is called kernel trick. So if we rigorously analyze the previous degree 2 polynomial feature or quadratic feature mapping, so for an n-dimensional feature vector, after feature mapping, the space of dimensionality becomes 1 plus n times n plus 1 over 2. Right? 1 is just the degree 0 term. N is degree 1 term, and all degree 2 terms after deduplication, you got n times n plus 1 over 2. So, of course, if you don't perform any kernel trick, you directly compute this feature mapping, the cost will be n squared, right? Time complexity and also the space complexity n squared, because you have to store such long mapped feature vector. But if you perform the kernel trick, right, we never need to explicitly compute and store the mapped feature vector. We do everything with the original feature vectors. So the time complexity becomes On, and space complexity becomes On. Right? So this is a benefit. So, any question regarding the kernel trick? Okay, so now we're going to talk about the properties of kernels. Okay. So for a kernel function, we'll view it as an inner product between two mapped feature vectors, right? A natural question will be, can any function of two arguments be a valid kernel function? And the answer is no. Right? Kernel function is just a type of functions with two arguments, but not all the two argument functions are valid kernel functions. A function k of x and z is valid kernel only if it corresponds to an inner product in some high-dimensional feature space. And the natural question would be, given you an arbitrary two-argument function, how can you decide if this function is a valid function valid kernel function? No. If it is a valid kernel function, well, I can just use that to perform kernel trick. We even do not need to know what kind of feature mapping it corresponds to. Well, to test if a given function is a valid kernel or not, here's the general idea. We're going to construct the so-called Gaussian matrix for an arbitrary set of inputs, and then test if this Gaussian matrix is a positive semi-definite or not. So what is Gaussian matrix? So we need to first review the concept called positive semi-definite. So this is a fundamental concept in linear algebra. Everyone should know that. And here is just a review. So we say a symmetric matrix M is positive semi-definite if for any non-zero vector Z, this quadratic form is non-negative. Namely, Z transpose MZ is non-negative. And Z transpose MZ, remember, it's a number, it's a scalar, it's not a vector. You can check that. If M satisfies this inequality for any non-zero vector Z, then we claim that M is a positive semi-definite. This is a very, very fundamental property. It's used everywhere, actually. And there has many nice properties about positive semi-definite, like all the eigenvalues of M must be non-negative. Otherwise, it won't satisfy this for every Z. Okay, so now, what's the definition of Gaussian matrix? For any finite set of vectors, x1 and xn, we can construct an n by n matrix G, where each element, Gij, meaning that the element at ith row and jth column, is computed by inner product between xi and xj. So this matrix G is called the Gaussian matrix. So Gaussian matrix is essentially a matrix computed based on a finite set of vectors. And their inner product, every element is just an inner product between two vectors. It's not hard to show the Gaussian matrix is positive semi-definite. Just needs a little bit linear algebra practice. It's pretty straightforward to show that. So the Gaussian matrix is always semi-positive definite, and this also applies to mapped feature vectors. Namely, if you perform some feature mapping over these n vectors, and then under this mapped feature vectors, you construct the Gaussian matrix. The Gaussian matrix is still positive semi-definite. This is called Gaussian matrix. So now, with the Gaussian matrix, how do we show an arbitrary function k of two arguments is valid kernel? Well, the direct approach was that, okay, you can find a corresponding feature mapping phi where the function value is just a dot product after performing phi. Right? This is the direct approach. But the more commonly used indirect approach is that you can use this function k to construct a kernel matrix on any set of vectors as well. So each element of this kernel matrix is simply the function k over xi and xj. So basically, the ith element, the ith row, and jth column, this element is obtained by evaluating your candidate function k on xi and xj. If you can show that your kernel matrix constructed from k is also positive semi-definite, then it means that your kernel matrix is a Gaussian matrix. And then your function k is a valid kernel. Right? This is natural, right? Because if your arbitrary k function you construct, it indeed corresponds to some feature mapping phi, right? And then you construct your kernel matrix. This is equivalent to construct a gram matrix with this underlying feature mapping. So if you can show that your kernel matrix based on the tiny function k is always positive semi-negative for any finite set of inputs, and then we can conclude that your candidate function k is a valid kernel. So this theorem is called Mercer's condition. Well, it's a very famous theorem in kernel learning. But as to how to rigorously prove that is not the scope of our class. Just to let you know how generally we can test a function is valid kernel or not. Right? So let k of x and z be a function that maps two n-dimensional vectors, right, to a real number, and k is a valid kernel if for every finite set of inputs. Right? If you construct a kernel matrix and for any choice of real values c1, c2, well, you can view them as a vector. Right? This double summation is essentially the quadratic form. It's a quadratic form like this. So this quadratic form is non-negative for arbitrary finite input, arbitrary finite set of inputs, and the arbitrary choice of coefficients here. It is non-negative, and then the kernel matrix is gram matrix, and then your function is a valid kernel. Any questions so far? All right. Here, we're given a set of commonly used examples for kernels, right? Linear kernel, just to do the dot product between the original input vectors, which means that you actually do not perform any feature mapping. Okay. Polynomial kernel, you just take the inner product between x and z and take the power of d. So this only reflects the disordered instructions, meaning that you just enumerate features in x and features in z vectors and combine them to ensure their product reflects d multiplications. And someone may think of like, why not I can expand them to reflect, to include all the lower order interactions. Well, it's simple. You just add up the inner product by some constant c and take power of d. Then this reflects the feature interactions of order d or all the lower orders. Well, meaning that it's like quadratic feature mapping, right? You have all degree 1 term, degree 0 term, degree 1 term, degree 2 terms, degree 3 terms, until degree d terms, and then you do the inner product. Here is a very common used kernel. It's called Gaussian Curve. Why it's called Gaussian Curve? Because the kernel function looks like the Gaussian distribution density. Okay? So you just take exponential to the minus this fraction, where the numerator is the square of the Euclidean distance between inputs x and z. The denominator is the c, is a hyperparameter c you're going to choose. Right? So sometimes they refer c as to the length field. So c, very small c will make your kernel matrix approximate an identity matrix. Very large c will make it like a unit matrix. You can try to look at it why this is like that. Right? So a very interesting result of the Gaussian kernel is that the feature mapping underlying this Gaussian kernel is infinite. So in our incoming homework 4, there's a bonus question, and encourage you to find out the underlying feature mapping for the Gaussian kernel. It's infinite dimensional feature mapping. So after doing that, you'll see why we really need Kernel Trick. If you don't have Kernel Trick, well, for the infinite dimensional feature mapping, you will never be able to compute it exactly, right? in practice. Okay, so given a set of knowing kernels, right, we can use a set of rules to combine them to get new kernels. So commonly use rules like you can multiply existing kernel by positive constant c, it is a new kernel. If you evaluate the inputs, the two inputs or two arguments of this kernel function by a function f and multiply them together, you end up with a new kernel. You can even use the kernel function's value to compute the polynomial. This is a new kernel. Or take exponential, it's a new kernel. Right? If you add up two different kernels function together, it will give you another new kernel function. They're all valid. Or multiply them together. Okay. Or you can make some simpler feature mapping first and then plug them into the kernel, a third kernel function like a Gaussian kernel, it corresponds to a new kernel, or some kind of multilinear result like x transpose ax star, and as long as a is symmetric positive semi-definite, this is also a valid kernel. So those rules provide you a way to construct even more expressive, complex feature mappings without designing those mappings from scratch. Okay, so here are the properties of kernel functions. Any questions so far? Anyway, kernel learning is a very big topic in machine learning. It's kind of like very in-depth mathematics because it relates to like representation theorems in reproducing Hilbert space and all kinds of stuff. It's very in-depth. But here, just to give you some kind of very, very shallow introduction about the key idea. Okay, finally, we only need like 3 minutes to introduce nonlinear SVM because we have all the things ready. And then to extend linear SVM to nonlinear feature space to make it much more powerful is very, very straightforward. Okay, how can we implement nonlinear SVM with Kernel Trick? So remember, you have a dual form, right? After a series of simplification, right? We solve our dual form in this form, right? And it's a quadratic function, where the objective function in each summon, this double summation, is just alpha I, alpha j, and then the inner product between x and xj. Okay? So now, assume that we conduct some nonlinear feature mapping, right, in a higher dimensional space with some complicated mapping fit, right? So in this new feature space, if you want to learn SVM, in our dual form, we need to replace this inner product by phi xi transpose phi xj, right? After feature mapping, we do the inner product. Now is the kernel trick. We don't need to explicitly compute feature mapping, right? We just replace the inner product between mapped feature vector by a kernel function here. So you can see that there's just a tiny change of the objective function. We replace the inner product between the original feature space by the kernel function. Then you are performing nonlinear SVM learning in some high-dimensional feature space. Does it sound okay? It's pretty straightforward, right? I mean, from a practical perspective, it's pretty straightforward. But why it can lead to this? Well, we need a long chain of the reasoning, I think. Okay, and remember, this does not change any property of optimization because we're optimizing alpha I and alpha j. And for this kernel function or this inner product, they're just constant values. Right? So as long as you can provide this, you can just optimize this with any off-the-shelf quadratic optimization library. Okay. So once you obtain the optimal parameters, right? By solving this field form, right? You got alpha I star and G star. You never need to recover the optimal B factor W. As we mentioned, right? We don't need to that. We just leverage the solution structure. We substitute the solution structure for this W. We know that the prediction score will be like that. Right? So it's a summation over all the training example where you need to calculate the kernel function between every training input and the test input, multiply with alpha I and y I, and then plus the speed. Of course, we need to recover B, right? But the recover B is almost the same as we discussed before, right? But remember, we need to find the feature. We need to find the training example whose alpha J star is strictly between 0 and C, right? Then you subtract the label yi by the inner product between W and corresponding feature input, right? And but W now is replaced by K. Right? So this is the same thing. So in your homework 4, you're going to implement a nonlinear SVM with different nonlinear kernels. And finally, we want to look into what does the margin and the hyperplane look like for nonlinear SVM. Right. So this is an example using Gaussian kernel. Right? You can imagine in some mapped infinite dimensional feature space. Remember, we just talked about like Gaussian kernel. The feature mapping is infinite dimensional. Well, in that infinite dimensional space, well, your hyperplane is just a plane, right? You got the margin, right? But if you project them into the original feature space, it becomes highly nonlinear. So these darker black lines represent the hyperplane in the two-dimensional space. I'm not saying in the high-dimensional space. In the original dimensional space. And those dashed lines are their margins. So you can see those circle points are the support vectors. Okay, hopefully this will give you an intuition about nonlinear SVM, and we have wrapped up the whole SVM topic. And on Thursday, our TM will give some more guidance about the Python libraries and debugging, and hopefully that will be helpful. Thank you.